Okay, sorry I wasn't able to make it. I was on the other line. Glad you could get here.
Yeah.
So we have sort of the first discussion scheduled and I said I'm going to be in your area tomorrow, so you should come on down. So great. So I don't know how specific this discussion will be through all the stuff we want to cover, but
hey guys, we're gonna get started.
So
Actual guest one word code case. Actual guest case one
Factual.
guest.
Oh, it is a factual.
Hey guys, so we're gonna get started. Thanks again for coming. Today we have Ryan, who's the CTO of VoltDB, going to give a talk on simplifying the Lambda architecture. Before we get started, a few quick announcements. Next Tuesday, we have another talk on Apache Ignite. It's an incubator project. It's a memory data fabric memory management project similar to Apache Spark. So if you're interested, you should attend that as well. The other thing, Big Data Day LA again, June 27th, just repeating it. Today was the last day for submissions. We have close to 60 submissions. So really great talks submitted. So you guys should definitely attend. June 27th, whole day of talks. We'll open up a registration in the next week or the week after. So you guys should definitely, it's completely free to everyone. So with and just Brian is going to come. Brian will probably do an introduction, but he's the CTO of VoltDB. Quick thing about VoltDB, they were one of our speakers at last year's Big Data Day LA. So I don't know if any of you remember Scott Jar, co-founder of VoltDB, actually came and gave a talk. So today we have Ryan, that's the CTO of VoltDB, come and talk more about VoltDB and how they are simplifying the Lambda architecture. Ryan, please give a warm round of applause for us.
You should wait till I'm done. You can decide if you want to applaud. Yeah, that's always wiser in my experience. So, my name is Ryan. Thanks for the kind introduction. I am one of the original developers at Volt. I'm currently the CTO. What I really love to do is work at very small companies making high performance middleware. So I've made all kinds of middleware. I've made VoltDB, a database. I've made like XML proxies, worked on frame relay, ATM switches. So my background is actually around fast middleware. I like to make tools that people use to make things, which is maybe not the way you should introduce a talk about complexities. It's not a particularly direct approach. But in the spirit of trying to make things simple, I've already been given a little bit of grief about the word complexity, so I'm going to be a little careful on how I use it. But in the spirit of making things simple, I can reduce all of interesting computer science to two things: computation and data. And this talk and all the things that Volt is interested about are really the intersection, right? So you can sit and compute things that don't need a lot of data. You can store a lot of data that doesn't need a lot of computation. But what happens when these things intersect? And you want to be able to apply computation to data. So it's not a novel idea, right? That computation and data are peanut butter and jelly. And we've been studying this for a long time. How many people here have made a database or make databases presently? Okay. Oh, that's awesome. So that'll be a lot of fun. So I suggested if you disagree or agree with what I'm saying, speak out. I'd love to have a conversation here. Last time I gave this talk, I gave it in front of a computer science professor. That was a fascinating experience for me. So there's really a number of things. If you make databases, you might know the Cow's book. It's a popular text in different studies. And it calls out a couple of the characteristics of what typically makes a good data management system. Data independence, sufficient data access, concurrent access, simplify application development. I don't like textbooks very well, and so I've also reduced this to three simple things. You basically need to store data, you need to make data readable and writable, and you need to handle separate users. You need to maintain some some separation between users. I will warn you that you're going to see this slide again later in the presentation because of a bug in Keynote. Keynote just shuffled some slides and made them invisible in the slide viewer. So this slide appears randomly throughout the presentation. It's neither you nor I am having a seizure. It's just there. So you have these three things. You want to be able to manage storing of data. You can make data readable, writable, and you need to maintain separation between users. And here on this slide, I have designed for you 48 different databases, right? You can kind of play mix and match book, and you can pick from each of these columns, then probably name a system that's been built in the last few years that has those particular characteristics. But you know, how each of these is important, and it's really, I guess the point of this is it's important when you design systems that have to manage the combination of computation and data at scale, that you understand why these trade-offs are important, and why these criteria, why these selections are important, because they matter. So for example, if you want to run a lot of queries across a relatively immutable data store, then you might want a column architecture, right? You might store your data columnarily or columnarly, depending on which company you work for. You use a different pronunciation. Because scanning data, you typically don't want to scan all of the records of a particular user. You just want to scan the dimension you're interested about, right? If I have a database that stores 200 facts about 300 million people, not an uncommon ratio in a lot of these systems, then I might want to know just everyone of a certain age and a certain gender and where they live, right? I only really care about 3 of the 200 facts. So I would organize the data on disk so that when I scan it, I don't need to uselessly skip over the 197 facts I don't care about and spend all that I/O. I'd like to just be able to read linearly the 3 that I would like. So I might store data in a column format. It's also important to understand that the way that we query data is different from the way that we store data. Right? There's an abstraction in good data management systems between the way that data is accessed and the way that data is stored. So both column stores and row stores offer an SQL interface. Right? And as a user, you might understand from the performance characteristics of the system that the storage is different. But from the interactivity, like the semantics that you have when you interact with that data, they're identical. You could write the same SQL statement against both systems, and aside for the vagaries of vendor SQL support, right, you would get the same result, but maybe with very different performance characteristics. And you can make really interesting choices. So the paper's kind of aging a little bit. One of my favorite data management papers is the Google Dremel paper. Right? It describes how they took a large collection of protobufs, right, documents, and mapped a SQL interface to that because their users demanded the expressiveness and simplicity. They wanted to reuse all the training they had around SQL. And so to make that data access interesting, it auto-generates little finite state machines to parse the protobufs in an efficient way, right? So you get choices at each of these different levels, and each of these choices matters. Data is very physical. You have to interact with it. You do I/O, so it matters how it's stored. Its physical access is important. You need to have some efficient methodology to turn the user's set of interactions into scans and accesses and filters of this data. And then you need to provide on top of that some semantic for the user to write an application against. And this, again, is separate from these two choices. Right? These are all independent choices. So traditionally, we offer ACID interfaces to databases. If you're familiar with any normal database, then you come at it from an ACID perspective. And ACID says that the key concern is separating users and applying rigor to business logic. Right? That's essentially what it says. Other people have said, no, that's wrong. I don't care about that. What I really care about is widely geographically distributed availability. And so they've chosen different query semantics, right? They've chosen base, which is just another way of saying eventual consistency, right? Basically available, soft state, eventually consistent. I still don't understand how those words just don't all mean eventual consistency, but some systems have tried to take a split, right? They've said, well, we started with a very eventually consistent system, but our users have work that requires a transaction concept, and they've introduced some kind of concept of a lightweight transaction, right? A compare and swap operator that you can use to implement some basic fundamental locks or some kind of quorum choices. So the point here is that this is what the Cows book is saying, right? That these things matter. Data storage, efficient access, and separation of users, right, are important concerns, and they're independent concerns. And you should think about which of these you're choosing when you choose a system to solve a problem. You don't know me well, but you will already have learned that I am horrible at speaking to slides in the order that they exist in the deck. So I've spoken to this slide already. This just says that what we chose to do through most of the 70s and the 90s is to build databases fundamentally for business applications where logical relational schema and ACID semantics that made it easy to express business logistics, right, were the most important choice. That was wonderful for a while, but all of a sudden, right, we hit a new set of problems. We invent the internet, and then for some reason we decide that everyone should be able to create a user profile on the internet. And that creates a whole new set of problems. So really, for a big chunk of the last 10 years, what we spent most of our time doing is a kind of community of practice of data managers, of data management systems designers, is we spent our time trying to figure out, how do I store a giant catalog? If you think about all of the work that was done to kind of make Web 2.0 work, all of it is basically, how do I store a giant catalog? Facebook is a catalog of all of the people on the planet, right? You can think of all the check-in companies as catalogs of all the places. There's maps. It goes on and on. And these catalogs far exceeded the capacity of all of the traditional relational systems, and it created sort of an explosion of new systems that made different trade-offs. These are the slides that are repeated. Wow, there's more of them every time. And so we kind of settled on a pattern for this, right? We looked at that problem and said, oh, well, it looks kind of OLAPy. It's kind of an analytics problem, and I can make a shared file system and put a bunch of data in it. And this particular problem has data that changes slowly. It's largely immutable. So how does that play out? And it turns out that in the design of these systems, the distributed file system component, HDFS, it has gained a ton of value, right? It matches the criteria, it matches this problem space really well. I didn't give credit at the beginning of the talk. I should to John and to Ning, two of the other core developers at Volt. This slide presentation is sort of a mismatch of their slides and my slides. So I don't have children, but this is apparently John's Pooh Bear. I think if I hit forward, it'll say HDFS. There we go. So the Pooh Bear is why is HDFS a Pooh Bear? So HDFS works because of the kinds of workloads that ran against it. Right? We had a lot of workloads that were just basically transformation workloads. You wanted to take one set of immutable data and produce what's essentially another set of immutable data. And if part of this processing failed, it didn't matter. You didn't do anything to the source data. You could just restart the process, right? This is just batch processing. So you took data set A and you applied programs that represented the culture and excellence of your programmers, and you produce another data set. Many things look like this. If you're making recommendation matrices, you're taking all of the interests of people and you're intersecting them, and you're producing, what other people might like by the intersection. Or if you're indexing the internet, you'll take data set A, all of the web pages in the world, and you'll run it through an algorithm that produces some weighted search index, right? Produce data set A prime. And if that process fails in part, it's easily restarted, right? And it's a batch process. So how does MapReduce, as a technique for running this batch process, map up against some of the original criteria? Well, MapReduce by itself is a relatively poor database abstraction. And I don't think that's controversial to say, because most people have already begun to walk away from it. And you can see that they began walking away from it almost as soon as they started using it. The first way they walked away from it was by saying, this is ridiculous. I'm going to put something in front of my raw MapReduce that generates MapReduce for me, but lets me speak in SQL terms, right? Hive or pig or something like that, right? So the first thing they did was they said, well, I need to pretend like, I can simplify application code. I don't want people writing raw Java. If you talk to a lot of users who've deployed large MapReduce or Hadoop clusters into really traditional businesses, like financial services businesses, they'll tell you that they're really upset that they took a lot of cheap business analysts that had nice tooling and had to replace them with expensive Java programmers. Now, personally, as an expensive Java programmer, I don't see the problem in that, but they do. So anyway, so MapReduce by itself isn't that great, but a lot of different SQL technologies have come along that have preserved some of the capabilities of HDFS, right? It maintained HDFS as the storage medium. We've invented file formats like Parquet to sort of, right, to make the data layer a little more efficient, and Google, right, a little more kind of engineering applied to this, has written things like Dremel that use FSMs to attack some of this data in an efficient way. And you're seeing all kinds of really interesting SQL systems emerge on top of these storage layers, whether it's Impala or Presto, or right, there's a whole suite of them. And they're really taking HDFS as a storage layer, and they're sort of building what looks like a traditional columnar OLAP system on top of it, right? So they've got columnar stored data stored at the file system level. They have a buffer cache. People are making nice in-memory caches on top of it. Spark does a lot of that. And then on top of that, they've written more and more sophisticated SQL planners. So this is great, right? We've managed to take really large data sets that didn't fit into our traditional databases, and we've managed to find a way to make them interactive for transformation and for analytics. But there's kind of a new problem. There's two reasons that you might have a big data set. One is you collected data that arrives slowly for a long period of time, right? And the other is that you've been collecting data that arrives rapidly for maybe a shorter period of time. And I wasn't, I kind of shamefully very aware of what Factual does, but I think here we're probably standing in a place that collects data that accumulates rapidly, right, over a short period of time. So at Volt, we really divide kind of the traditional big data world up into fast and big. And we do this for a couple of reasons. One is because we make a product that fits nicely on the fast side, and we like to draw the distinction. But the other is, I think, useful. There's a cycle that you go through with large data applications. First, you collect data. You try to gain some wisdom from it. We might call that data science, right, if we're writing resumes. Otherwise, we might just call it hacking if we're having fun, right? And eventually, we prove out some hypothesis from our data set. We find some set of user segmentation or user behavior. We find some model that informs a more efficient process. If we could apply that model to the new data that's arriving in real time, we could do something interesting. That interesting thing might be as mundane as contextual marketing. It might be real-time resource assignment for a really constrained resource. Maybe it's something more life-saving, like you're going to make sure that a nurse doesn't walk into a hospital room with a drug that a patient's allergic to, right? You're going to catch that in real time. There's all kinds of applications that you can use, that you can build, where you can take the sort of the wisdom that you've gained from your large data applications and apply that using a model that you've derived from these analytics to a real-time application. But again, how do you do that? Right? This is a bad map to HDFS for a number of reasons. One is it often is a time-bounded process. There's really a couple of different time bounds in these fast data applications. The first is you need to be able to make a decision that's in line with the user's experience. So everyone who builds commercial web properties understands that users are very latency sensitive. Users will wait a couple hundred milliseconds, and after that, they notice a degradation in experience, right? And your engagement with that user degrades. So in many cases, you have to be able to make some kind of a decision, a recommendation, an authorization, a customization, or a personalization in a relatively tight latency budget, a few handful of milliseconds. And obviously, you can't do that with a batch processing motif. The other thing that's interesting is that oftentimes, the decision that you want to make is based upon real-time contextual data in combination with the model that you derive from your analytics platform. And I have a favorite example of that, as you might have expected. So when you play a free online game, what is the game player doing? They're trying to make money, right? That's what we're all trying to do. So how do they do that? If you don't pay for the game up front, they need to maintain your engagement in that game and bring you to a point where you make a decision to spend money. The most important thing for the game platform is to maintain your engagement and to understand when it's appropriate to offer you something to purchase. It needs to drive you to some kind of a player journey that ends in a revenue event, some reasonable probability. So how do you do that? What's important? It's no longer important then that John and Joe are playing identical games. What's really important is that John is playing a game that he enjoys and that Joe is playing a game that Joe enjoys. That means that the game platform can tune gameplay individually for John and Joe in real time. I don't like really complex games when I'm tired late at night. I prefer games in which I can progress relatively easily because I'm lazy. And that means that if I'm playing and I'm stuck, that game platform may have identified me through their analytics in the back end as being in a segment that prefers to move through games quickly. They combine that with contextual real-time information to understand that in the last 30 seconds, I have failed to get more than 60 streets on Crossy Road. And so maybe they'll make the next level easier for me so that I can progress, that I remain engaged, and I'll eventually be led to some kind of a revenue event. That's kind of a trivial example, but you can see the same example play out over and over and over again. For example, I have a list of customers that I've determined are at risk of changing from my service to another service. How could I use that list in real time so that if one of them calls my help desk, I can guide them more proactively through the IVR, right, to get to an agent at priority. Immediate customer service. So applications like that are obviously poor matches to batching, and they need to combine a couple of different components. The real-time analytics to understand that contextual state, the model that you derive from the HDFS portion so that you know what behavior you're trying to incent from this particular user or device, right? And the ability to make a decision, right? To run a transaction that combines these two pieces of information with a new event in order to send back some parameterization to personalize or customize whatever process is being written. And so how do we do that? Well, I love this slide. This is a John slide. You may already be wishing that John were here and not me when you look at this slide because of its considerable cleverness, but alas, you have me. So a lot of times, just like we go through a cycle around big data where we collect and we analyze, and only then do we know how to build an application that drives value from all of that work, a lot of times the same thing happens on the real-time space as well, on the fast data space as well, right? We start with analytics, right? The first thing that we want to do is often just count something. How often did this happen in the last few seconds, right? Who's the hottest group right now? Can I draw a heat map? Can I calculate real-time key performance indicators? You know, one of Volt's customers has an application that anyone in their office can connect to their Wi-Fi, pull out their iPhone, and they can see in real time how much revenue their platform is generating, right? Within the last second, right? Just kind of very simple counting. And it's a tool that's used broadly by everyone in the company, even a sort of a real-time concept of how well are we doing. Eventually, you know, they may want to begin to build some personalization, kind of a transactional process against that. But their first challenge was just solving this streaming analytics problem. So a lot of people call this kind of the Lambda problem. We call it the fast data problem. I tend to use the word streaming aggregation. How do you approach a solution to this? Well, I think we've trained ourselves to do something that is not so clever, right? We have learned how to go to the Apache website and download tarballs, and then we've learned how to build Scrum teams to try to wire them together. Or we solve an amazing number of problems this way, or sometimes we fail to solve some number of problems this way. And the rest of this talk is about some of the advantages and disadvantages of this approach versus an approach that takes the perspective of think about how you build a data management system and what the quality of that data management system might be, right? Kind of back to the initial topics. So a lot of times people assemble the kind of ZKSC stack, and this is sort of, I'm going to kind of describe how this is Lambda, but different audiences know these things differently. Are people familiar with this stuff? I won't repeat it if people are not. Okay, so these are all Apache projects. They're all good projects, and they're very, very useful. And they get wired together to solve real-time analytics problems. So what are the components of a real-time analytics problem? Well, starting from the far left, I'm horrible at left, I turn around. That's great, Ryan. So starting at the far left is Zookeeper. Zookeeper is a distributed log manager, right? It just basically manages the state of everything. It's kind of the truth teller. What's the state of my services, and how do I manage kind of subscriptions among them? How do I advertise them? How do I make discovery work? How do I understand which ones are running and which ones are not? Right? It's just sort of state management. Kafka is a distributed queue. It's a very fast, high throughput distributed queuing system. Storm is a stream processing system. Storm lets you take a little bit of Java code and plug it into a framework called Storm. And Storm will take an incoming event feed and effectively partition it across a large number of servers that are all running your little snippets of Java and then you just build a pipeline so that the input of one snippet can be the output of one can be the input to the next, right? Or in fancy terms, it allows you to build a directed acyclical graph of computation, right? And Cassandra, I think most people are probably familiar with, is a NoSQL system. So how do people wire this together for real-time analytics? I really have no idea what's going on with this slide deck. Well, kind of Nathan Mars coined this term Lambda architecture to describe how you might use this kind of an infrastructure to solve real-time analytics. And what the Lambda architecture really says is that you can divide this problem into a few different components. So the speed layer is sort of a set of tools or a set of like tools that we were just talking about. The batch layer is your OLAP, Hadoop, Vertica, Teradata, Presto, whatever it is that you're using for OLAP analytics. Then you can use a common serving layer. This would be sort of Cassandra in the previous example. And you can do two things. As new data arrives, you can pass it through what's really a computation pipeline, right? You can hand code a bunch of Java to do the aggregations and computations and summary that you want to do. Of course, you can't query any of that, right? It's just a bunch of code. It doesn't have a query interface. So every now and then you can kind of spew little sub-results up to the serving layer, and then this can be your query point, right? That's kind of what the Lambda architecture says. So if you, you'll have to just forgive me for the slides. If you look at that, what is this saying? Lambda is basically saying, well, batch is too slow. Right? That's what we're kind of discussing. These are real-time processes. They're latency constrained. It's fast-changing state. And streaming systems traditionally have kind of been crappy. So how do I fix that problem? I'll do both at the same time. Right? It's kind of what Lambda says. I'm going to use OLAP to kind of give historical summaries. I'm going to use streaming to hand calculate new summaries, and I'll combine them together into a shared layer. So how does this line up against some of the criteria that we're setting out? What are the problems and complexities in this? Well, one is that data is owned by multiple systems. Now, when we think about Hadoop, we're very used to assembling a large number of tools together, but we kind of lose sight of the fact that there's really one tool that owns that data, right, that owns different immutable sets of data that are being created through effectively batch or OLAP query processes, and that's HDFS. I mean, that's a really important aspect that makes that system work. I see some people who maybe don't agree with that, but if you think about how does my OLAP system work, if you're using Hadoop, right, that system, what's the system of record, right? There's one system of record. It's the data that's in your file system, right? No? Yes? So this isn't true in the streaming system. In the streaming system, ownership for this data is passing through a number of different components, right? First, the queue owns the piece of data, right? Then the Storm pipeline owns the piece of data, and then the Cassandra pipeline owns the piece of data. And in parallel with that, the batch system, right, also received that data and probably also calculated analytics off of that. That's another piece of data. And all of that data got combined into a serving layer so that I could actually let a user interact with it. Because data that you can interact with is just a discarded hard drive, right? It's the interaction that makes it valuable. So this is a really different point, and it's a very subtle point, right? If you don't look at how these systems interact, and if you don't try to manage them and deal with fault tolerance among them, it's not always obvious that this is happening. So for example, one of the most common complaints with architectures like Storm is that fault recovery is quite difficult. If you're generally creating little batches of information and kind of posting those aggregates out to a serving layer and something fails, what do you need to coordinate? You need to coordinate at least 3 different components now to recover from that failure and resume to a consistent point of computation. You need to be able to know what data in my queue do I need to replay, right, through the computation system. And you need to understand, oh, well, okay, I'll chop my data into generations, right, or into some units because that's the chunk of summary that I'm posting out to my serving layer. So now I need to understand, well, what generations have made it to my serving layer and have been persisted at whatever the fault point was, right? And then I need to tie the generations that made it to that serving layer to the generations in the Kafka layer. I have to truncate the generations in the serving layer back to a point where I can replay right into the computation stream, and then I can restart my processing. Right? So I had to look at multiple systems, understand their state at a point of failure, and then from that, reproduce the replay stream and the truncation point right on the persisted side that brings me back to a consistent state. That is a really, really different recovery story from what happens if my MapReduce job dies. If your MapReduce job dies, you just start it again, right? Because it didn't change anything. And the data that you're running it against is probably largely immutable. But here, you don't have immutability on your side in the same way. This is the key complexity that we would like to try to address. I don't know why the good admiral is on this slide, but we'll say hi to him as he goes by. So there's another point here, and that's that you have many different systems. Each is a distributed system. Distributed systems tend to need at least 3 things to run, right? Because they need to reach agreement sometimes. This means that no matter what size your problem is, even if your problem is relatively small, but maybe too big for a traditional database, that you end up running 12 or 13 different nodes, right? Different servers. You need to manage all these different systems. And what I see is that there are organizations that have made running things like this a main competency. They're large organizations. They have large and well-established DevOps groups, and they're running many of these things, and they're very good at it. And there's not a lot of additional overhead for them to add 3 more, right? Because it's not like they're going from 0 to 12, which is much harder than going from 1,000 to 1,012, right? But there are many organizations that don't have that infrastructure and that don't think it's valuable to build that, right? They would just like to have a set of smaller, cheaper, more efficient machines that they can use to write reliable applications in a relatively efficient way. So this is kind of where we're at when you use Lambda. You can see that it really doesn't meet as a concept any of the different data management system requirements. An easier way to say this is that if the main source of your computation is 100% divorced from your layer of storage, you haven't really built a very useful database, right? Databases are all about bringing computation and data together, right? Through these 3 different concepts that we were talking about at the beginning. How do I store data so that my I/O pattern is efficient? How do I parse that stored data in a way that's efficient and maps to an expressive query language? And what semantics do I give to users to write applications against? Right? We haven't done any of that in Lambda. Lambda describes a system of computation, but it doesn't really describe a system of data management. And that's an important difference. And so Lambda doesn't offer you any data independence. Everything that you're doing is hand-coded and hand-parsed. Right? The data management system isn't taking any responsibility for the format or storage or layout of that data in some efficient way. That's all on you. You don't have particularly efficient data access. There's no SQL planner that you're running that understands a cost model that's going to make access to your data efficient. You have to understand that yourself and basically handwrite what would be the equivalent of your SQL plan and then deploy that into a network attached set of computation nodes. There's a number of inefficiencies there, right? The fact that there's a network between them, the fact that you have to do the job of the SQL planner, the fact that you don't have a cost model to apply. So for example, if you want to join 2 things together, a SQL planner will understand the cardinality of the 2 different sets on the 2 different sides of the join. It'll execute that series of joins in a way that's efficient based upon the cardinality of the sets. Here, you would have to understand that yourself and do it for yourself. Concurrent access, there's really no query model, right? You can't query the computation source. You can only query the final aggregates. They're often stored into NoSQL systems that have poor query interfaces. That's not their core strength. They have a lot of nice core strengths, but query interactivity isn't one of them. And you had to write a lot of custom code, right? You're right back to the core challenge of MapReduce. If you go to someone and says, I want you to use MapReduce, they're going to say, but wait a minute, I have 100 people here who know SQL, or maybe more likely, I have Tableau, and I would like to use that to generate my SQL. And now you're saying, well, you know what you need to do, dear customer, is just go hire a team of people that understand how to write really high efficient, networked, fault-tolerant, distributed software, and you'll be able to count, right? That's basically what you're saying. So how do we make that better? Well, the first way to make it better is to stop and understand what's really happening in the system at a slightly, maybe more academic level. If you build a DAG, if you build a a storm or a stream processing system, right, or some kind of acyclical graph processing tier or workflow tier, you'll recognize that there's really a few key operations that you implement. There are a few fundamental operations. You can filter, join, aggregate, order, and project. Right? Filter just says you're good, you're bad. Right? Join says I'm going to evaluate a predicate and decide if these two units should be merged together into one. Aggregate, fancy way of saying count. Ordering is sorting. And projection is the reorder or materialization of a tuple, right, by applying an expression to another tuple. Well, where have we seen these terms before? Right, this is SQL, almost by definition. In SQL, filter is just where. If you want to filter something in SQL, you just say you write a where predicate, and I want everything greater than 5. I want every talk that Ryan didn't give, whatever your expression is. Join is join. Aggregation, SQL uses different terms. It says group by min and max, right? Or more modern SQL engines will have what we use analytic expressions, right? You can get row-wise grouping without aggregation, but it's another form of without group. You can get row-wise aggregation without grouping. Order is order by, and in SQL, the keyword for projection is simply select. So certainly there's nothing that this DAG is doing. There's nothing that Storm or any streaming system. I just use the word Storm, I'm not picking on it specifically. These all have the same characteristics. There's nothing it's really doing fundamentally as a unit of computation that the SQL system doesn't do. It is doing it in a different way and without efficient access to data. But there's another component that we would really like to keep. There's actually something very clever happening in the Storm pipeline, and that's that it's maintaining streaming aggregation. It's maintaining a continually up-to-date count or summary of the state that's seeing. And this is usually very often the main workload that you're trying to accomplish at first in these systems. You want to count impressions, you want to count interactions with some unit, you want to be able to know which devices have touched your service most recently. And so this we would like to keep in our system, right? We would like to keep the ability to maintain a result, an aggregated result as we move along. So let's talk through something a little more concrete. This is another John slide. I'm actually not a big fan of trench warfare metaphors, but when vendors go to talks, when vendors listen to talks, I think vendors listen to talks very differently from users. That if you're a user and you go listen to a talk, and another user, another of your peers is saying, we did this thing and it was crazy hard, but we persisted, right? We put our nose to the grindstone. Here are the clever things we did, right? There were the hacks that were beautiful that made it work. You're like, that's pretty awesome. I like that. When you're a vendor, you think you have two thoughts. You think number one, like, wow, I'm doing a really bad job of making the world easy for people, right? You take it personal, like you had to do what to make that work? And then the other thing you sometimes ask yourself is like, well, why didn't they use X, Y, Z? That would have solved their problem with a lot less work. So we listened to a talk that poor Ed, who is actually a very nice person, so he gave about building a Lambda architecture to count unique devices that are seen on mobile operating systems. And so his challenge was that he gets about 800,000 events a second, and he wanted to keep a summary of what device IDs had been seen on or what applications had been seen on what devices. And Ed's end goal wasn't all that complex. Ed just wanted to draw a simple chart. That's all he wanted. But it turns out that drawing a chart that changes 800,000 times a second is actually a relatively complex chart to draw. So he applied some statistics to this problem. It turns out that if you take the number of devices in the world and the number of applications, that storing the intersection just through pure brute force, although maybe Ed didn't have all of the knowledge of factual, it is hard. It wasn't something he wanted to do. So estimation was fine for Ed, and so he applied hyperloglog. Hyperloglog is a nice package that basically does cardinality estimation. It has a simple interface. You ask it, it's like how many times have you counted something, and it'll give you some error-bounded result. And when you would like to add a count to something, you just update it with the number of things that you counted recently, right? So basically update and retrieve. And this was the system that Ed built to do this. So Ed combined all of these different services together to produce that graph. right? And all of the consequent problems that we walk through and inefficiencies. So pros and cons. Pros, it's pretty scalable. There's a lot of shared nothing, horizontally scaled stuff in there. So if you want to do more, you can start more servers, have more CPUs, more network bandwidth, and do more processing. You know, you are doing all of the work twice. You're doing it once on the batch layer and once on the speed layer. You could call that a pro or a con, but it's self-checking, so that's nice. It is recoverable in a case of failure if you do a little bit of work to be able to understand where you stalled in the pipeline and which of the different components witnessed what results before the failure occurred. And it's all open source, so it's certainly not cheap as long as you have the development expertise to build it. But it requires lots of nodes. It's not efficient. You can process with many fewer CPUs at higher efficiency. You're doing a lot of work twice, and the failure model is, honestly, I think the failure model is almost impossible to understand. There's so many different parts that can fail in so many different combinations. But what do we do? Last time I showed this slide, people looked at me and laughed. I'm not sure why, but but you're nicer. Oh, look, the slide repeats again. So what do we do? So let's stop and look at what kind of a data management system might solve this. Can we take sort of the idea that we gave at the front of this talk about what makes it a nice database, and can we look at this particular problem of computation and data, and can we tie something to it? The first thing to understand here is that I like to think, what would you do if this didn't happen 800,000 times a second, but happened 10 times a second? Right? If this happened 10 times a second, would you solve this program by passing all of the computation through some set of stream processor and storing partial results into a database? Right? Probably not. Right? If this happened 10 times a second, you would install MySQL, right? And you would call it 10 times a second, and you'd be done. Right? So why not be able to do that at velocity is the main question. So here's a database that does this, and this database is Volt. You may not be surprised to learn. But Volt does this in a way that's really different from a traditional database. And I want to talk through that and kind of discuss why database semantics are actually the appropriate semantics for a problem like this. So fundamentally, counting something is a transaction, right? But we still want to maintain the ability to run some user code, like that hyperlog code. It's a really nice third-party code. We'd love to be able to put that code close to our data, run that code directly in our database, right? That's a nice feature. We should keep that. And we'd like to be able to respond back to events, right? A lot of these applications are one-way data in, but many are generating responses out. And anytime you have a system that puts a queue and a stream processor in front and behind of one another, you're losing any kind of synchronous response characteristic. And we'd like to be able to interact with the state that's accumulating with the serving tier using traditional tooling. Right? We'd like to be able to run SQL or Tableau or ODBC or JDBC against that set of aggregates, against that set of collected analytic results. And we'd like to be able to use that and expose it to users. And we'd like a simpler failure model. So how can we do that? Well, there's some things that are very similar. So the previous system, all of the computation was in memory. Or if you're running a Storm cluster, all of the Storm processing is likely in memory. Even if you're keeping cache state on a per node, per kind of Volt basis, you might use something like Redis, which is still in memory associated with that. So we can keep an in-memory processor, and we can run Java logic directly in the database if we express that Java kind of as a stored procedure. So we can take third-party Java code, we can treat it like a stored procedure, and we can freely mix and match something like hyperlog with SQL for data access, and we can offer fully ACID semantics for the user programming model, hyperlog for the estimation that needs to be done in this particular example, and then as we use the materialized view concept to seal that, as you reuse that, you can be maintaining aggregations as these different events are seen by the database, and you can offer a full SQL interface to them. Okay, so now you've done a couple of different things, all of which align nicely to the first part of the presentation. Right? You've decided how to store data. I'm going to store my data using something that looks kind of row-wise and relational. That's the efficient access path. I'm updating, in this case, little hyperlog blobs over and over again. So a row-wise fast retrieval of that is nice and efficient. I am maintaining an ACID programming model so that the unit of work in this stored procedure is guaranteed to be isolated and independent from any other work that may be happening concurrently in the database. Right? These won't be stomping on each other. More concretely, if you want to be able to update a value, you need to be able to read it, decide if you want to update it, and write it back. Right? There's 3 or 4 different accesses to that piece of data, and you'd like to make all of those atomic and isolated. That's not something that happens in many systems. So I'm going to speak through some of this. So what does this app look like if you deploy it into a database versus into a stream processing system or into a Lambda style architecture? Well, the first is that you get a schema, right? You can express the data that you would like to store. Before, this was all basically stuff that came out of your hand-coded Java, right? There wasn't any schema. You had to create this, right, through some kind of set of hash maps or something internally. And here you can just say what you would like it to be. You can index this in different ways. You can distribute this across a cluster, right, by partitioning it. And then you can operate against it using a combination of Java and SQL. Here's just a little snippet of what that might look like. So this is a Volt stored procedure. Volt, a stored procedure, is a Java run method that takes parameters, and it can mix code with SQL. There's a SQL statement here somewhere up here. So what is this doing? So this is a transaction, right? This is one fully isolated piece of logic, and a Volt cluster can execute a piece of logic like this 1,000,000 times a second, right, on an appropriately sized cluster. Not a large cluster either, fewer than 20 nodes. A single server could do this 100,000 times. And an environment that has built-in fault tolerance and availability with it, like the other systems we were discussing. So what is this doing? Well, first it takes an input. Basically, here's something to count. It grabs the hyperlog data from the app, from the database. If it wasn't there, it makes a new instance. It updates it, right? It just says, please count this for me, Mr. Hyperlog. And then it writes those bytes back to the database so that they're persistently stored and available the next time you want them. And it updates some state. Now you can write any SQL you want, right? And you can go query those hyperlog events, right? You don't need to go and change the DAG to count something new if you'd like to be able to mix and match the results of those counters. Your serving tier and your computation tier are unified, right? You've moved your processing close to your data. That has a lot of efficiency and fault tolerance benefits. So there's a couple of things here to point out, and these are questions that people commonly ask me. What are my feelings on consistency versus eventual consistency? So I think in many cases, eventual consistency is very important. If you're building something where availability of a user's data is of primary importance, but the accuracy is of secondary importance, right? If you can tolerate availability of something versus correctness, then it's fine. But in any application like this, where you're really trying to produce a count, or where you're trying to maintain some kind of analytic result, it's much easier to do if you have something that's consistent. What I find is that when people set out to build a consistent system, whether it's on Mongo or Redis or HBase or Volt or Rethink, if you start to list out who's chosen consistency versus not, you'll see that a lot of the popular players offer consistent interfaces because developers like that. That you can develop your application often like 3 to 4 times faster than you can against an eventually consistent system. I've seen this very, very commonly, that people will start and it'll take a year to develop something that maybe is eventually consistent, right, with rich semantics, and it would take them a few months to do the same if they had consistent semantics. So the point here is it's not that there's anything that you can't do with eventual consistency if you're willing to push enough complexity to the application and teach yourself how quorum semantics work and how to structure all of your applications as logs that get merged, right? But that these things are much, much easier to do in a consistent system. So for example, this example, the hyperlog app counting example, is relying on estimation. But there's some portions of this data that you could keep with perfect accuracy. So maybe you care for the first number of applications that you see per device, or the most used applications you'd like to keep a perfect count. It's only for the long tail that you're willing to estimate. Or maybe you'd like to keep a perfect count for the first 5 days and then roll that into estimation after. right? All of these things are easy to do if you have a consistent system. So there's been a number of different parts of this talk, but I think that the main focus here is that when we make choices on how we want to solve the combinations of computation and data, when we make choices about how to deal with that intersection, let's stop and think. Let's think about what systems have served us well, what systems have served us poorly, and ask why are the systems that have managed to win and maintain dominance over decades been successful? What are the core characteristics of those systems? I think for databases, it's kind of the list we've been walking through. And then as you try to assemble a new architecture, just pause and ask yourself, are you throwing those things away? And if you are you doing it on purpose? Maybe you are doing it on purpose. And if you have a good reason, then I'm certainly not here to stop you. So my thoughts for the day, I'd be happy to start a conversation or ask your questions or ask questions. But thank you for your time.
I feel like there's something important here. Like it looks like in this application, a big chunk of the problem is solved by using hyper workload.
Mm-hmm.
And otherwise, it looks like a regular SQL application. So can you pinpoint exactly why it's possible using VoltDB and it's not possible using MySQL?
So it's not possible using MySQL because of the frequency of the input. So this particular application had to count almost 1 million events a second. And you can't really post 1 million multi-statement transactions against MySQL in a second.
And where is roughly VoltDB magic that allows this to happen?
So what's the magic behind Volt? That's a big question that I'm happy to answer. It's a long answer. So essentially, Volt does a couple of things that allows it to do this. So Volt was architected by Mike Stonebreaker, Dr. Stonebreaker, who created Ingress and Postgres and Vertica and Streambase. And when he architected Volt, it came from the idea of, okay, I can take a system like Vertica and it can be 30 to 100 times faster at analytic workloads, OLAP, right, online analytics processing workloads. That's nice. And so what would I do to design a system that had that kind of performance improvement over a general purpose system, but specialized towards transaction processing? And so the result of that system, the result of that architecture is what Volt became. And Volt makes a few key choices that are very different from traditional databases. So the first is Volt puts all data in memory. Your entire data set is memory resident in the memory of a cluster. Right? This works because in many cases, transaction processing problems, the data set that you need to store to transact is usually based on the number of users.
Because your data set is small as well.
Exactly. So that's, yeah. So that's the first point. So the second point is that if you take a traditional database and you put it fully in memory, and then you do instruction counting, you say, well, what parts of the architecture of this database spent time? Where's the time spent running a query in the database? It turns out that about 10% of the time is spent running the user's SQL. Right? The other 90% of the time in that database, even when it's fully memory resident, largely goes into durability and concurrency management. Because just because we're putting our data in memory doesn't mean we're giving up durability. Right? All of like Volt and right in the system, they're all still durable to disk. Right? Volt maintains an image of all of its data on disk. And it turns out that concurrency control, managing separation of users, I think was the way I put it in one of the early slides, is really expensive in traditional systems. So the way that a traditional database does that is it has some shared piece of data, and it uses complex hierarchical locking to guarantee that users will see some isolated view of that data. And those locks are really expensive on modern computers because they require memory coherency across sockets. Volt does something a little bit different. Volt kind of takes the processing model of something like Storm, although Volt was designed years before Storm. But it takes that kind of a processing model and says, let me process event by event, right, with processing each event from beginning to end, right, without any other interruption. So let me basically do serial processing of a queue of work versus concurrent processing to a shared resource. And it turns out that by doing that, Volt can process tens of thousands of events on a single core. It can expand that model, right? Just take that model, kind of rubber stamp and clone it across cores within a server to process hundreds of thousands of events, millions of independent SQL statements on a server, and then kind of rubber stamp those servers into a cluster to get to a point where you can kind of process millions of independent events. So Volt reimagines a few different components of a traditional system. One is it puts all the data in memory, which is typically fine. Your observation, this isn't a lot of data, is correct. Two, it re-architects the way that databases deal with concurrency. It orders work and executes work serially in order versus allowing contention to a shared resource. And then finally, to make that work, Volt doesn't allow end-user transaction control. So a traditional database, a user can say begin transaction and can have multiple interactions between the application and the database, and then can decide if they'd like to commit or roll back. In VoltDB, when you present work to the database, the work you present is essentially a transaction. It could be a stored procedure, invocation, or a single SQL statement, or a REST API call. This is actually really common, and almost all NoSQL systems do this. Like if you use Mongo, you can't open a transaction in Mongo and execute a bunch of different API calls, right? You kind of execute one, and that's a transaction. It's kind of doing the same thing, but with a SQL model. So that's how Volt is different.
It's fair to say that for this application, when MySQL, there will be contention on this application ID. We still in separate incoming servers would be trying to update count for this application ID that would be locking.
So my feeling, and I'm pretty upfront about this, is that if you have a problem at a scale that you can solve with something that you believe and trust in, like whether it's MySQL or PostgreSQL Server or Oracle, then you should, right? I'm not interested in that. But what do you do when you have an application that doesn't meet the scale of that particular system? So you have a couple of choices. One choice is you might just shard that system, right? You might deal with sharding on yourself, put that burden on you, and continue to use a storage system that you have a lot of faith in and just manage sharding complexity at the application tier. A lot of people did that.
The question is more like, I don't have faith in MySQL, but you have a SQL database here, so prove to me that it's better than the system in which I don't have faith in.
Yeah, so
that's kind of the question.
So part of the point that I'd like to get across is that these different systems are great at solving different problems. Right? MySQL is really great, I think, or Postgres or whatever your traditional database is, at the things that we've been using it reliably for 20 years now. But what happens when you want to do something against a really high velocity data feed? If you'd like to be able to support an application that's making transactional decisions at really high frequency, how do you support that application? And so the question here is there's really two different ways that you can approach that. One way to approach it is with a set of systems, a queue processor and associated databases that sort of pair it all together. And the other is to look at that as an OLTP processing problem and approach it with a database that's designed to be really efficient at OLTP from the ground up. So these aren't really being positioned as replacements to traditional technology. These are tools that are useful to solve a new class of problems. Are there other questions in the back?
I recently heard another one of these talks about hacking Druid, which also seems to says it's encapsulating the Lambda architecture and its persistence and capabilities. I'm wondering how that might play.
I look at Druid as more of an OLAP system. So Druid is taking data and it's compressing it kind of on a time series basis, and it's not really storing the kind of raw row-wise data. So Druid isn't good at running a lot of user transactions, right? But Druid is excellent at storing a bunch of time series data and allowing you to query across that time series at different sort of magnification levels at different points along that. Volt would be not so great at that. Volt might be able to do that if you structured the application well and kind of knew what ranges you wanted to look at. Volt would require you to kind of do a lot of pre-aggregation to solve a time series problem like that. But the way that Druid stores data, right, kind of going back to the bottom tier here, the way that you store data is important. Right, so Druid is architected to store data in a way that makes queries across the range of a time series really efficient. But that choice makes it very bad at transacting against that data. All of these OLAP systems that sort of chop data up to make them efficient to query, they make it harder to run a transaction. It typically wants to compare one or two full records to each other. That's the trade-off. So that's how I think about it. All right, well, thank you, everyone.
So thanks again, guys, for coming. If you could just help with moving the chairs and putting the tables here, that would be great. Appreciate again. We'll be posting a video of this on the website as well as the slides too. Thank you. bring the tables out here and just put the chairs around.